Hi students, in this final video for online lecture 4, we are now going to talk about emission spectra. So what is an emission spectra? There are different characteristic lights that are emitted by elements when a voltage is put through them. So as you can see here, I can take a high voltage, and when I put it into a discharge tube containing one of our elemental species, it is going to shine a light. Some elements have a distinct light, whether that be yellow or blue or purple or red. But then what happens is if we take a slit as well as a prism, we can separate those colors into their various components. These individual lines that you see are now going to discuss electronic transitions. So if we look at the hydrogen atom, we are going to see 4 characteristic emission lines for the different electronic transitions. We see one here at approximately 650. We see one at about 480, as well as about 410 and 430. Now, these are not the only electronic transitions that occur during the emission or excitation of hydrogen, but these are the ones that we can observe due to their energy and their coinciding wavelength and frequency being inside of the visible spectra. So now we can look at the line emission for elements that are going to possibly be very indicative for them and very helpful for our identification. Many spectroscopy methods also use this, as well as what is commonly known as the flame test. In a future demo video, you are going to see that when elements are heated, they are going to emit a certain color. But that color could be the constructive interference of many different excitations. So let's go ahead and look at the alkali metals first. You can see that lithium has really 2 visible emissions, one in the reddish orange and one that is orange. Sodium has 2 very distinct yellow emissions that are very close to each other. Finally, you'll see that potassium has not only a couple of red, but they also have one down in a purple transition located at the very high frequency locations. If we go to the alkaline earth metals, you will see that there are more visible electronic transitions. As we start to go through all of the various groups that you'll see, you will notice that there are more transitions for species that have more electrons. This means that electrons can jump from different orbitals and be excited, and when that excitation happens, when they relax, they are going to give off this energy. 2 species that we want to talk about at the very end are neon. You have probably heard of neon lights, made famous by Las Vegas, and in many cases during the 70s and 80s, were very important in marketing and on billboard signs. Notice neon has distinct groups of obvious transitions, some in the red, some in the orange, 2 in the yellow, a grouping in the green, and finally some in the blue. So now what was happening is they were saying, well, how can I get purple neon colors? This must be just like Crayola, where we can mix our red and our blue and you would get purple. But that's not the case, because seeing that these are done by electronic transitions, blue and red are very far apart and have very different excitation energies. So what can we do? Well, finally, during the late 80s and early 90s, they started to use argon as the purple when dealing with our neon lights. So they used to call them neon lights because they were typically neon. But if you saw purple, this was actually argon and would need a higher excitation. So as you see here, we are seeing some of the electronic transitions. But how do we actually promote and see this on an electron by electron basis? Well, we can look at it using the Bohr model of the hydrogen atom. Bohr was the first person to really look at the electronic structure. As we saw in the previous chapter, we talked about the structure of the nucleus and how we figured out that the protons and neutrons were in the nucleus, but that the electrons were in the outside. The Bohr model started to really look at how these electrons are organized. First off, Bohr stated that electrons can only have specific quantized energy values. These energy values would coincide with known distances away from the nucleus. So this means that the quantization of our energy comes from how far the electron is from the nucleus. The second idea was that light is emitted as energy moves the electron either up from a lower energy level, and we need to see how that determines in many cases. So let's look at it again. Light is emitted as electrons move from one energy level to a lower. So as we are adding energy to an electron, we typically call that excitation or a promotion. We are moving it from one orbital to another. But that is a temporary state. Those electrons would prefer to go back to where they were, releasing that energy, and that is our emission. So when we are seeing our emission spectra, we are not seeing the promotion of the electron, we are seeing the resulting emission of that energy as it relaxes back to its original state. The energy, as Bohr put it, is equal to this negative RH times 1 over n squared. N is our principal quantum number. This is going to have integer values of 1, 2, 3, so on and so forth until we get to approximately 7 or 8. RH is commonly known as the Rydberg constant. This is a known value for hydrogen as the amount of energy that it takes for an electron to move to another principal quantum number. That value is 2.18 times 10 to the minus 18th joules. So let us look at our model for an electron-electron basis. As I like to call this diagram reminds me of Neil Armstrong walking on the moon. We have one small step for man, one giant leap for mankind. So let's talk about our one small step for electron kind. Notice that if I make a small step, that would result in a small amount of energy being released. This is going to be a quantized amount. You will see that that electronic transition is colored red because that is the lowest visible energy that we can see. So now let's talk about our one giant leap for electron kind. Now you can see here that it is a bigger jump. Our electron is jumping 2 stairs, which is 2 energy levels, and it's a much bigger leap. This means that there's going to be more energy released. So as you can see here, the photon that we release is going to be colored green because it has more energy coming off to do that step. So as we start to emit our energy going from an excited state back to the original ground state, if those jumps are very close, little amounts of energy are going to be released. If our jumps are very big, then you will find out that we are going to have higher energy photons released for this case. So now what this looks like, and an easy way of calculating this, is using what we commonly known as the Rydberg equation. So as you can see here, the energy of the photon is going to just be the difference of the energy. So that is the final energy minus the initial. For an emission, the initial energy is going to be higher. Then we are going to lose some energy to get to our final energy. In the case of a promotion, our final energy will be higher than our initial energy. We can use Bohr's idea and say that the final energy is equal to negative RH times 1 over our principal quantum number squared for our final state. We can also do the same for our initial. Let's take these two equations and plug them into our top equation, and you are now going to get what is commonly known as the Rydberg format. That is saying that the change in energy for our electrons is equal to RH times 1 over n squared of our initial state minus 1 over n squared of our final state. Now, one of the things that happens here is this looks like it's initial minus final, and that can get very difficult, but notice that you are taking the subtraction of a subtraction So now a better format of this would actually be having the negative come out front with the final and initial flipping. So as you can see here, for the Lyman series, if I go from 2 to 1, notice that that is a fairly big jump. But I can go from 3 to 1, 4 to 1. But now let us go ahead and talk about the really important series, and that is the Balmer series. From 3 to 2, because our energy difference hits that perfect visible spectrum, if you get a transition from 3 to 2, you are going to emit red light. If we go and transition from 4 to 2, we will get green light, so on and so forth. Our Passion series and our Bracket series actually have a problem, and that is the fact that their transitions are so small that they are going to have non-visible emission spectras. So in this case, when we have the emission spectra for both the Passion series and the Bracket series, they do occur. And this is why for our emission spectra, we only see certain light, even though there are many, many more electronic transitions. It's because these occur in our UV situations. So in the case of the Lyman, these are going to be UV present. For our Passion and Bracket series, these are going to be IR visible. So this is going to be an issue. We are only going to see certain transitions as we go through our examples. So let's try one of these examples. What is the wavelength of a photon in nanometers emitted during the transition from our N initial to 5 going to our N final of 2? So the first thing that we want to do is go write our equation. We can have our delta E equals our Rydberg constant times our N squared initial minus our 1 over N squared of our final. So there's our equation. So now let us go and plug in some of our values. So our Rydberg constant is 2.18 times 10 to the minus 18th joules. And now for our values, we would have our initial squared, so that would be 5 squared. So we can say that that's 1 over 25 minus our 1 over and our final 2. We need to square that, so that would end up being 4. And we are now able to calculate our change in energy. If we do this, we are going to see that our change in energy is equal to negative 4.578 times 10 to the minus 19th joules. So now you're probably asking about the negative. The negative is showing that this energy is being released. So what is gaining that energy? Well, that's going to be our photon. So now what has to happen is we need to say that our change in energy of our photon is equal to the negative change in energy of our electron. So now what we can do is go and change the sign for our delta E. Well, back in the last video, we also said that E was equal to HC over lambda. So now we can say that our energy of our photon can now be used to calculate the wavelength. So let us go and do that. So we have our H, which is Planck's constant, so that's 6.63 times 10 to the minus 34th joules times seconds. We have our speed of light, which is 2.998 times 10 to the 8th meters per second. And then finally, we are going to take the positive value for our energy and go and switch our species. So notice that I am just flipping the location of our energy and our wavelength. So this is going to be 4.578 times 10 to the minus 19th joules. So notice that my joules and joules cancel, my seconds and seconds cancel. I'm left with meters. That is a good unit for my wavelength. So now I can say my wavelength is equal to 4.34 times 10 to the minus 7th meters. While this is a correct answer for meters, it actually asks for it in nanometers. So what I need to do is go and say 1 nanometer is 10 to the minus 9th meters, and you will see that my wavelength should end up being 434 nanometers. This is going to be in the visible spectra, and you would be able to see this as a bluish purple color. In this video, we talked about electronic transitions and how electrons will move from one orbital to the next because of energy being put into our atom. Once that electron has gone to a higher state, eventually it will relax, giving up that energy, and that is what you see in the emission spectra that we have talked throughout this video. In the next few videos for the next lecture, you're going to see how further electronic calculations will show you the importance of what the electrons do in our atoms. Have a great day.